Okay, so I'm going to talk briefly about two experiments. Of Summit Birwa and then of Ganga Prasad. This is joint work with Narayanan Menon at UMass Amherst. Okay, so the first experiment is a very simple one. You take a ball, drop it, and ask what happens as it nears the floor. So there's three things that can happen. One is it could drop down and you have viscous flow surrounding it, very viscous fluid surrounding it. So then the first thing that could happen is that the viscous fluid slows it down so much that it slowly comes to a rest. The next thing is it reaches close to the ground, doesn't quite hit the ground, bounces back and then slowly comes to rest. And the third is it collides with the ground and then goes back and bounces back. So we are going to ask about which case happens. So then, will the ball touch the floor? That's the basic question we've asked here. Drop a ball, will it touch the floor before bouncing? So then, as it comes down, you can see that there are several forces acting on it. One is the viscous drag acting on the ball as a whole, and then there's weight minus buoyancy acting downwards. And in addition, you have a wall force which is coming because the fluid close to the wall is getting squeezed out as the ball goes down. And lubrication theory says that the ball will not touch the floor because the pressure will diverge as the height goes to zero. The pressure will diverge and then you will have you'll have a force which more than balances the weight at a place at some finite height, and it will bounce without touching the ground. So we wanted to test this in experiment, and Sumit just designed this experiment where he has a ball falling. Basically, it's metal on metal, and there's a electromagnet which shuts off, and you can make the ball fall from different heights. And we actually can test for electrical contact between the ball and the floor. And this is what happens to the voltage. So we're proving beyond a doubt that the ball is touching the floor, and it has a little time of collision and then it rebounds again. So wherever you see a voltage, the ball is touching the floor and then it comes to rest. So this is just one typical kind of experiment I've shown you. In the experiment, we have a very viscous fluid. I think it's glycerol of various things, and then put the metal ball. So so this is what the time of contact is, and this is what the flight time is. So this is just an example result I'm showing you. So you see that when you drop the ball at different heights, you get different Stokes numbers. And with different Stokes numbers, you get some kind of pattern. This pattern is not always this beautiful. This is with an etched ball. So you see that the next flight time is in milliseconds, and the first contact time is in microseconds. And so to understand, to come up with a better theory which doesn't look like the ball is never touching the ground, we don't have yet a touching answer, but we are looking at this better way of writing the flow profile very close to the wall. So the earlier theory had assumed a lubrication approximation. They'd just put in a parabolic velocity profile, and then they'd said it will never touch the ground. But we are trying to do it by a better approximation. It's a boundary layer approximation, and we are allowing for weak non-similarity. We are allowing for the profile to do what it likes, and then we are allowing for it to change with radius. And so we get this very complicated equation, which we then solve, and we show that suppose this is the ball and this is the wall, and we count the radius from here, the r from here. At low r, you get a parabolic profile which was assumed in the lubrication approximation. But higher r, of course, the gap is bigger, and you get a reverse velocity flow profile. So you get a completely different flow profile itself, and this is more correct than the parabolic assumption. So this was the velocity versus height by the parabolic assumption, and we are getting this. So we are showing that as the height goes very, very small, the velocity is definitely different from the lubrication approximation. So by the next community meeting, I'll have an answer for this. And let's go to the next one, which is Ganga's experiment. So he also looks at solids and fluids, but he now has flexible filaments on a fluid interface. So like what he does, so you're now looking at the top of a beaker. So there is glycerol in the beaker, and we have this flexible filament made of some vinyl polysiloxane. So this filament is sitting on the interface. You're looking at it from the top, and I'll try to show the movie. Oops. Yeah. What we've done is we've started out the filament in a bent position. It doesn't like to be bent, so it's opening out. But then there are viscous forces acting on it which slow down its unbending. So it's a combination between viscous and bending, but there's an important thing which is happening, which is the tension inside the filament itself. The tension within the filament is changing the answer. So if you do a linear bending analysis like most people do, you will get completely the wrong answer. So we have to do a nonlinear analysis of this problem. So then if we non-dimensionalize by this time scale, in this time scale, the length is of the whole filament, B is the bending modulus, mu is the viscosity. So we divide the thing by this time scale and write out a force balance. You get a parameter-free nonlinear equation. And that's very interesting. It's completely parameter-free. So like we have done some assumptions for the drag over here, and we've put the constraint that the length of the filament has to be conserved. And so you can solve this parameter-free equation, and you are most satisfied by a perfect matching with the experiment. These are all numerical results, and one particular shape is matched with the experiment, but all the shapes match. There is a mismatch which I'll come to. So what we've done is this experiment, we've done over 2 different kinds of Young's modulus, many different thicknesses of these filaments. So we've actually changed the factor tau, the non-dimensionalizing time scale, by a factor of 26. So we've done a whole bunch of experiments, and then we're plotting this distance, which should go basically to the length of the wire. And we're plotting that distance non-dimensionalized versus this non-dimensionalized time. And you see a collapse over all the data, which is over a factor of 26. Now, this line is the theory line, but we have cheated by changing the time scale a little bit. So that's because there's some differences between the experiment and the theory, which I can answer later if you like. And these are particle image velocimetry images where you see the vortex forming. This is very slow flow, mind you. And then you can see the fluid resisting the unbending of this. So the thing is that the experimental relaxation time is faster than the theory, and both are much faster than the time scale tau. Notice here that we've scaled it by a factor of 100. So effectively this thing opens out extremely fast. And the reason for that is the tension. The tension is not uniform. The tension and the bending, they subtract each other to give a very small number. This small number then balances the viscous force. So because the tension is different at different places, and because it's very high, this is basically the effect of nonlinearity. And that makes the thing open out much, much faster. So there's effectively a very large prefactor there which comes due to tension. There's the asymmetry thing. So now what you do is you take that droplet and you take that filament and you take it on the surface of water this time, and you put a drop of mineral oil. And then you ask what happens to this filament. Like, we remember that it didn't like bending. This time we made it so much thinner that it doesn't mind bending, doesn't quite so much mind bending, but it's now going to look at this mineral oil droplet, and it will, because the mineral oil hates water more than it hates the filament is going to be forced to bend. So it will give some, it will sacrifice some of its energy state to minimize the net energy. So the interesting thing that happens here is that Normally, when a drop sits on a solid, it subtends a Young's angle. The contact angle is given by the Young's angle, but in this case, it will not subtend the Young's angle. So this angle, the nu, which is the line between this and that, and the line between here and here, theta plus nu is not going to be equal to theta y. That's the interesting thing you can find here. So basically, the filament is so tiny, it's not easy to see, but you see that we are able to change the tension on the wire, on the filament itself. If the tension is very large, it subtends Young's angle. So here is the large tension limit, it subtends the Young's angle. At lower tensions, it subtends an angle which is much bigger than the Young's angle. And that's the angle it subtends. So that's the sum of the two angles I told you about. And again, we get a collapse over a very large number of, like different filament thicknesses, different, materials. We get a collapse of this data because we've divided the tension by a critical tension. The critical tension is that needed for a zero bending energy guy to close in on itself. So the way this filament, we've actually calculated this tension exactly. It's actually in micronewtons. And we've done it by, the filament I showed you the last time, we put that filament as a small beam. And we solve the nonlinear problem for the beam to get the exact tension. And that enables us to get this clean collapse. And that's the end of my talk. And please take home these messages.
Questions?
Bounce the ball. Is there also a deformation? I know that it might not be an elastic substrate or elastic ball, but in principle there should be
metal ball and a metal plate, but there is deformation. There is deformation. When they come very, very close, the pressure is so high that something does happen. And finally, when the ball hits the metal plate, you do form craters. So we've done some, analysis of this and how it changes. But the theory doesn't account for that.
I have a stupid question. So your first equation that you showed us of the ball is not supposed to touch the ground. You had an h dot of t in the numerator.
Yeah.
But isn't that going to become zero as you, after multiple, isn't it going to slow down?
So the result shows that the h dot doesn't go to zero. So basically it's coming at high speed. And as the height goes to zero, the pressure is diverging. So the h square in the denominator is doing the job.
No, but I'm just saying...
doesn't go to zero.
I'm just saying naively.
Yeah.
Naively you said that, but I was saying even naively that, isn't that false? Because h dot will become zero eventually, right?
Yes.
So eventually...
definitely before it turns around, h dot will become zero.
Yeah.
But the scaling thing shows that the h is going to zero faster.
Okay.
So yeah.
That's the point.
Yeah, like physically what will happen, we don't know. We've solved those equations and you're getting distances of nanometers which are less than the roughness. Yeah. So it's basically a pedagogical question, you can say.
So I guess the filaments here are kind of doing like in the overdamped limit. Is it like the inertia is not so important?
Yeah. So the Reynolds number is extremely low.
So is it also possible to do experiments where you can see like inertial effects?
Yeah. So basically we need filaments which hate bending so much. Their bending modulus is so high that they will snap back. And you can also reduce the viscosity of the fluid. So you can do experiments in that limit.
And so in this case, what like the relaxation time, do you have an estimate of like how it depends on the whatever elastic constants, and I don't know what it depends on.
So basically the elastic constants, everything gets clubbed into one time scale.
So you can get a time scale, but if there is much,
it doesn't match by a factor of 100, and that's like a non-dimensional prefactor which is deciding it. It's not like any of the physical things in the problem. And that's because the tension that builds up inside the inside this filament is so strong that it affects effectively a snapback relative to what you expect. And that scales with the exact same time scale, but with a different prefactor.
Yeah. So is this like bending and unbending? Can you make it reversible in the sense it bends and opens? And
You
thinking of something like a scallop. I mean, can it move if you do that?
So basically, like to make it bend again, you have to apply an external force.
Yeah.
Because the equilibrium situation is an unbent one.
So if you do that, I mean, do you think because of the elasticity,
Will it move?
will it move? Because scallop is, it will not move because it will, because of the scallop theory.
So if it's inertial, we can make it move, I guess.
Okay.
But if it's very in the viscous limit,
Yeah.
probably it will just go back.
Okay.
Okay, let's thank the speaker once again.